Okay, what is really important is that we start connecting what we've done now so far in the finite element method back to our first year physics. Think about, okay, so we're applying loads to structures. So there are the forces that we apply are doing work on the structure, and that work must go somewhere, and it goes into strain energy into that structure. We don't have any damping, so there are no losses. So what we want to see and expect to see is that the strain energy that is stored is equal to the work that was done. Otherwise, there's energy gets destroyed or disappears or gets generated, and we can't have that. That is not going to be okay. So this is again just, we want to make sure that these basic physics and physical principles hold. And so I'm relating this now back really to our first year physics to a large extent. Okay. So let's think about this and see. Okay, so this is now our structure. We have clamped it here. It's a one length, 1000 newtons applied area, Young's modulus. And what we've done is we've solved now KQ equals to F, and this is the solution to the problem. Remember, to solve this, we had to reduce it to this 2 by 2 system only for the unknowns Q2 and Q3. Q1 was known because it was 0. And now we have everything reconstructed. We have the full F vector and we have the full Q prescribed, or the full Q loading. That is what we have now. Displacement vector that we've computed. Okay, so that's it. Okay. And now we can ask ourselves, okay, so F in this case clearly depends on Q. Okay. So if F changes, Q changes. There's some dependency about that. So if I want to compute the work, I have to say, well, work is just our definition for work is just the integral of our force over the path which that force acts. Okay, so over the displacements. So this is really what it is. So F, which is a function of Q, we just need to integrate over Q. Okay, from 0 up to Q, the value that we have. That is important to understand. And so in order to do that, we can say, well, we know what the relationship between Q and F is. It's just F is equal to KQ. So that is our FQ relationship. And this is what I want to integrate. K is just a constant. Okay, so the integral of KQ over Q is just a half Q transpose KQ. This is what it is. Okay, and we could write it in a different way to say this is equal to half Q transpose F, because KQ is just F. And this is essentially what it means. The really important observation here. So this is really important. This is what the work is done, external force. It's not, you can't omit the half there. And the importance of this is it tells us how we should think about the load that we apply, because we're applying a load, let's say initially at 0, and we think that essentially that load gets ramped up until we have the full load magnitude there, because that load is essentially what it's telling us. It's like a spring that we are loading from 0 up to a certain point. Okay, so because that F is not just 1000 newtons I put down and boom, I get the Q out, and so I just say, oh, the work done is Q transpose F without the half. That is the wrong interpretation of work done by external forces. And this is important to take note, because this is something that often might be done wrongly. Okay, sometimes even experienced engineers might make this mistake. So the finite element method tells you how to think about the external loads. KQ equals to F. So this tells you the forces that we apply. We should think of something that starts at 0 and gets ramped up to the magnitude. It's not just the same magnitude independent of the Q that we had. This is really the model for what the relationship is between forces and displacements. Okay, so that's essentially what we see here. And then I can say, well, strain energy, we know we can compute the strain energy is just the integral of epsilon transpose sigma over the volume. So this is sort of a standard relationship for strain energy that we've done in W8L1V2 and MSY310. So this is this tells us if we do this integral, we get an idea of what the strain energy is in the system. And let's see what happens if we do this. So we know what the relationship for stress, we know what's the relationship for strain. We can just plug those things in there and say, oh, stress is BQ, strain is BQ, but we can, strain transpose is just Q transpose B transpose, and that's that. And so what we see is we can pull out the Q transpose and the Q there, because they're just constants. And then we have the integral of B transpose EB over the volume. What is this? Oh, this is just our stiffness matrix. So the strain energy is just a half Q transpose KQ. So any displacement vector that I have, I can just multiply, pre and post multiply to K, or with K, and then multiply by half. And that's the strain energy. And what we say is that the loading that I've applied must be equal to the strain energy. And I can see that by just looking at it. Because there is what I derived, half Q transpose KQ. The strain energy is also half Q transpose KQ. And I've computed the strain energy from the definition of strain energy to say that essentially this is the same. Okay, that's important observation. It's a one-pager, but it really is just to make sure that we relate strain energy back to work and see that everything makes nice sense, how these things are nicely related to each other.